many of you may be like, magnets, they're really cool, but how do they relate to life sciences? How do they relate to biology? And you're going to see there's a million connections, but one of them that I think is fascinating is that there are actually very simple, very small bacteria that have used magnetic fields to navigate, and they're called, unsurprisingly, magnetobacteria. Okay, so magnetobacteria use a chain of magnetite crystals to orient themselves with the Earth's magnetic field and navigate. If these creatures are sensitive to magnetic fields as small as 25 microteslas, how close would they need to be to a power line to sense the magnetic field due to its current? To pause right there and just kind of help us appreciate that when we leave a footprint on the Earth, like, for example, just making power lines that go everywhere, suddenly we're confusing a lot of life, right? Any of these bacteria that are within this distance that we're going to calculate in a second here, they start becoming confused and think, it totally overwhelms their sense of the Earth's magnetic field because it becomes stronger than, or at least on par or sensible with respect to the Earth's magnetic field. So just something to think about. Doesn't mean we live in a world where we don't embrace technology at all, but just to kind of understand what the effect that technology does have on some of the life around us. All right. The average current of a power line is about 700 amps. What does your answer say about the effect of human technology on the natural world? All right. So how do we do this? Well, we say that there's a power line, right? And it has a current in it. And the current is 700 amps, as it says, right? And we want to find out if there's like a little magnetobacteria that uses these little magnetic crystals to kind of orient itself to the Earth's magnetic field. How far does it have to be able to sense it? Okay, so it can sense 25 microteslas, right? So what's the formula for the B field as a result of a current-carrying wire? Well, as you remember from the last slide, it was that B equals mu naught I over 2 pi r, right? But am I looking for B? No, right? I know that this fellow here is sensitive to 25 microteslas, but I want to know how far do these power lines have to be away from this magnetobacteria in order for it to feel the effect of the power line. In other words, I'm really looking for R, this distance here, okay? So R equals mu 0 I over 2 pi b, okay? So in other words, how far does it have to be? 4 pi times 10 to the minus 7. Remember, mu 0 is 4 pi times 10 to the minus 7 times the current going through this wire, which is 700, over 2 pi times what is the magnetic field that it can actually detect? Looks like 25 microtesla. So that's going to be 25 times 10 to the minus 6 Tesla, right? And I get an answer of 2.6 meters, right? In other words, roughly 7 to 8 feet, right? So if these power lines are within 7 to 8 feet of these bacteria, they can detect the power line, and it's going to confuse their navigation and their orientation. Luckily, power lines are generally much higher than that, so that effect isn't extremely felt by such magnetobacteria. All right, but cool. We've now officially used, within like 20 minutes of one chapter of a physics course, okay, we have been able to find out the effect of a man-made current on life on the planet, these little magnetobacteria. I think it's pretty neat. There's quite a bit of power that can be derived from just a little bit of knowledge. Cool. All right, moving on to the magnetic field due to a solenoid. Okay, so this is a long straight wire, but a long time ago, scientists realized they could get a lot more bang for their buck. Okay, a lot more magnetic field if they made something called a solenoid. What is a solenoid? Well, a solenoid is basically a coil of wire. So let's imagine that you have like some core there that you can wrap something around, right? And then you would have like all these little loops, and it's wrapped around, right? Now, if there's a current in here, current current, 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 right? If we use that same right-hand rule, right? So I'm, pointing my thumb in the direction of this current. That means that there's going to be a magnetic field that like wraps around and comes back out in this direction. So all on the inside of this coil, it's going to be all these magnetic fields pointing in the same direction, 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 pointing in the same direction. They're going to all add up. It's a little magnetic field, little magnetic field, little magnetic field, little magnetic field. That adds up to one big magnetic field where this is like a North Pole, this is like a South Pole, North Pole, and South Pole. Cool, right? That ends up being, because it's not just one current carrying wire, but like, many current carrying wires, it ends up being much more powerful. And so how do you calculate the magnetic field inside of a solenoid, inside this coil? Well, it's simply just this formula. B equals mu naught times N times L, times I. Okay? So in other words, permittivity of the magnetic field in free space times N, which is the turn density. Okay, so N is the turn density. It's the number of turns, right? The number of coils, the number of loops per unit length, all right? Times the current going through that wire. So one more time, you have mu naught, the permeability of magnetic field in free space, times the turn density, the number of turns per length, right? Which either you count it or the problem gives it to you, etc., times the actual magnitude of the current moving through that wire, all right? So let's show in a specific example how this can be so much more powerful than one actual wire. Okay, so let's take the example of one of the largest magnetic fields ever produced, which was 37.2 Tesla. A Tesla, like a Coulomb, is actually a tremendously large unit of magnetic field, right? Remember how we talked about 1 Coulomb is actually a whole lot of charge, even though it's just one? 1 Tesla is a whole lot of magnetic field. 37.2 Tesla is astronomical, okay? So that's one of the largest magnetic fields ever created. It was achieved at MIT, Francis Bitter National Magnetic Laboratory. And I want to find the current needed to achieve a 37.2 Tesla if you're 2 centimeters from one straight wire or at the center of a solenoid that's 32 centimeters in length and 40,000 turns. Okay, so let's look at part A first. Okay, so what current would I need? Well, remember, we have B equals mu naught I over 2 pi r, right? That's the formula for a current carrying wire. I want to find out what current, so I'm solving for current, that's going to be 2 pi rb divided by mu naught, right? And I want to achieve a 37.2 Tesla field. So I'm putting that in for my B. And it's going to be 2 centimeters away, so 0.02 meters. All right, over 4 pi times 10 to the minus 7, I get a current of 3.7 times 10 to the 6. 3.7 times 10 to the 6 amps. That's 3.7 million amps. That's huge. That is a huge, huge current. There's not a whole lot that on Earth that makes that big of a current. Okay, that takes a tremendous amount of power, especially to run for a while. Now, how much current would you need if instead it was a solenoid and it was 32 centimeters in length and 40,000 turns? Okay, well, let's erase this. Okay, remember the formula for a solenoid is this: B equals mu naught N I, or we can say that that's mu naught, the number of turns times the current over the length of it. Okay, so if we want to solve for L, or for I now, right, it would be I equals B times L divided by mu naught N. Right? Okay, what magnetic field do we want to make? 37.2. How long is it? 32 centimeters. That's 0.32 meters divided by 4 pi times 10 to the 7. and it's 40,000 turns, so we put 40,000 here. Okay? In that case, I get a current of 237 amps. Compare that to what we had before. 3.7 million amps versus 237 amps required to make the same magnetic field. All right? It just shows you the power of having a solenoid, the power of creating a magnetic field using this coil as opposed to just one straight wire. And for those of you who, in the Mythbusters lab that we do later in the semester, if the project that you pick is to make your own electromagnet, this is exactly the technique you use. You make a solenoid. You wrap a insulated wire around like an iron core, like a nail or something, hundreds and hundreds and hundreds of times. That creates a much larger magnetic field. All right, so that is a little deep dive, a little exploration into how to create magnetic fields and how to calculate them, whether they are a long straight wire with a current or whether it is this little coil thing called a solenoid. Okay, both create magnetic fields, and calculating them is pretty basic. Solenoids create stronger magnetic fields. In the next video, we're going to flip it a little bit. We're going to talk about what force does a magnetic field exert on a moving charge inside that magnetic field. Okay, so moving charges create magnetic fields, but magnetic fields can also exert forces on moving charges, and that's what we're going to explore.